Hello, we're starting with chapter 11 now, and we're talking about state diagrams. So this is an idea that will take some time to get confident in using, and it's kind of a different concept, but we want to talk about how to write programs with using state diagrams as the background or the base for being able to write these programs and techniques for doing that. So we start out with the question, what did Della wear? Well, she wore a brand new jersey. And what did Missy sip? She sipped a mini soda. And on and on and on it goes. And we basically talk to you and say, we're confusing you. And this is kind of a strange way to enter a chapter, but it's the wrong kind of state. We're talking about state diagrams, and hopefully by the end of this chapter you'll understand what the word state diagram actually means, and you'll have a little bit better idea as to why they're so important in development of PLC programs of any kind, but specifically we'll talk about some of the applications and where they're used. So this is something that we use in this chapter and we use in succeeding chapters, and we've actually talked about it in prior chapters. We talked about state diagrams a little bit in chapter 8 when we're talking about numbering the steps and that type of thing. So we're into this already, but we just didn't realize it. And sometimes it's better to introduce things kind of a little at a time, and that's what we've done here. We've introduced things a little bit at a time. So you can rest assured that nobody has ever programmed a state diagram really just as a state diagram. They've always programmed it in a ladder programming or some other language, but state diagrams have formed the background for a lot of different applications. Sometimes it's almost trivial, and in a case like this one, it is. I would not use a state diagram for this application, although you can use a state diagram if you want to, and you can make a state diagram for this. This is a filling station, where they've got a cart, and you've got a conveyor belt, and you've got some material coming out of the silo, and you're going to fill this cart wagon. But again, you don't have to use a state diagram for this unless you want to. If you want to, you can. This is a check of how you could do it, and you could actually start at home, then start the belt, then open the slider, then start the filling, and close the slider, and then stop. So you can do all that if you want to, and if you want to picture a state diagram for that, go for it. It's not what I would do. It is just one of those things where you say, okay, and then go on. It doesn't help you. But again, sometimes state diagrams are of no help. Sometimes they're of a great help. Sometimes a real simple state diagram is of huge help in defining how a process is going to run. So again, I don't want to scare you off, but I want to tell you that sometimes it's not a big deal. Okay. Now here is an item that if you see these, think state diagrams. Pneumatic cylinders and state diagrams are very, they work together very, 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 very well. So basically, if you have a bunch of these cylinders, pneumatic cylinders or hydraulic cylinders, but basically pneumatic cylinders, you probably will be benefited by using state diagrams. So what does this thing do and how does it work? Well, it works a number of different ways, but basically there's two ways you can use a state diagram. One is single acting, where there is a spring working against the air. So if you push air in, it pushes the cylinder out. And if the air doesn't come in, then the spring pushes the cylinder back. So basically this cylinder moves in and out based on whether or not air is pushing in or not. So there it is. That's single acting. And here is double acting. So here you push one way and it pushes it this way. You push the other way and it pushes it back. So that would be a double acting cylinder. But basically these cylinders have two positions. They have where you're at the left, where they're at the right, or you can be moving left or moving right. So that gives you really 4 states for a cylinder. So anytime you see a cylinder, you can say, ah, I have a four-state diagram, and you would be right. That's what you have. It's not a big deal, but it's something that you can pretty well take to the bank. Anytime you have a cylinder, you can have one of these. Now, is that all you need? Not really, but it can be all you need if you just have one cylinder in your program. If you got more than one cylinder, they interact with each other. And when they interact with each other, you can have more complicated state diagrams than just this. But this is a starting point. Sometimes we have two cylinders, sometimes we have three cylinders, sometimes we have more than that. Sometimes we have something that is entirely different from cylinders, but anytime you see a pneumatic cylinder or a hydraulic cylinder, but especially a pneumatic cylinder, you're going to find state diagrams are going to help you, probably, with your programming. Okay. So, you have to pick a programming language, obviously. And in this case, you're going to be looking at specific stations and that type of thing. So we're going to also have a recovery set of state diagram, and also a homing sometimes for state diagram. Now, here is a state diagram that you may have not even thought of as a state diagram, but when you were doing the project at the end of chapter 8, where you were doing the two's complement calculation, you were doing a state diagram. Whether you realized it or not, that little bit called flip, that bit that was set, that either you didn't flip the bit or you did flip the bit, is a state diagram, because you're in the state where you do not flip, or you're in the state where you do flip. And this is an example of that. So you're either over here or you're over here. And once you go over here, you stay here until you're done. It may not mean much to you in this example, but some people, it means a lot to say I'm in this state here or I'm in this state, and then basically you see yourself, I'm in this room or I'm in this room, and they see that as a help. Sometimes simple state diagrams are of great help. And this is the program for that. So you set the bit, or you didn't set the bit. All right, so here's another one. It's a simple program, but it isn't so simple until you see a state diagram aspect of it. So here we have boxes that are being loaded onto this conveyor. You push the button, the boxes go over to this conveyor. As soon as you get 4 boxes on this conveyor, they march off of that conveyor and they go to this conveyor. So basically, this conveyor can either be used as a loading conveyor or as an offloading conveyor. So it's in the loading conveyor mode or it's in the offloading conveyor mode. Now, what causes it to switch? Well, when the count goes to 4 on this conveyor, from this photo eye, it flips from a loading conveyor to an offloading conveyor. So we go from this state here to this state here. Then as you march the boxes off of this conveyor onto this conveyor, they go 3, 2, 4, 3, 2, 1, 0, and then you go back to when the count equals 0, and this goes back to a loading conveyor. Now, I know that some of you are going to say, but sir, can't I be doing both? Can't I be loading while I'm unloading, that type of thing? It's possible, but if you want to keep this spacing of these boxes, you definitely don't want to do that. You want to treat this as a loading conveyor or an offloading conveyor, and it gets into the idea of what we call the KISS method, K-I-S-S, keep it simple, stupid. And if you are really interested in making this a simple process, it's either a loading conveyor or it's an offloading conveyor, and you flip a bit that determines which way you're going to go. And if you see that, if you see it as a state diagram, it makes your programming of this application much, much, much more simple. And it helps to eliminate a lot of the what ifs when you're programming if you can see that I'm an loading conveyor or I'm an offloading conveyor, and it helps a lot in programming. So it gives you a little bit of a comfort level that you can actually simplify big programs, make them a lot easier if you see that. Okay, so what happens if a bee flies by one of those photo eyes, or a big bee hovers over one of the photo eyes and trips it? Well, obviously your count gets off. And in a situation like that, sometimes you either have to just take all the boxes off and start over again, or you have a reset button someplace hidden away that does the same thing. If you have an HMI panel, you might actually put a little bit of an extra diagnostic in there that says, I've got 3 boxes on this conveyor, I can accept a 4th box or whatever. Something to get you going again if you get out of whack. But typically, as long as you're working with most systems, these photo eyes are very robust and they only see what they're supposed to see, and you don't get that kind of a problem. However, if something bad happens, you do need a way of getting out of it and getting on with life, and that's many times a reset button. So again, you have to plan for the bad as well as the good. Okay. We are going to look at a program at the end of chapter 13 called Simon Says. It's a game, but it also has a state table for it. We're either not playing the game, or we're playing the game showing the lights, or we're playing the game with the person pushing the buttons. If they win the game, you flash the lights and you go back to not playing the game. If they made an error, you just go back to not playing the game. So we talk about it in depth in chapter 13, how to program this, but the first step is to be able to see this as a state diagram. Okay, so there are other methods that you've seen before that may help you with the idea of state diagrams. One of them is the idea of sets. You're either in this set or that set, or Venn diagrams. And we talk about them both in mathematics courses and logic courses. But this would be a Venn diagram of the game Simon Says. You're either not playing the game, you're either showing the lights, or you're pushing the buttons while you're playing the game, and when you're done, you push the flash the lights showing that you've won. So this would be a Venn diagram. So some people talk about state diagrams, some people talk about Venn diagrams. They're the same basic thing in this kind of application. So you can see either way works. Now there is a language that is called sequential function diagrams or sequential function charts, and sometimes is called SFC, sequential function charts. It's a graphical approach to state development, and it is something, and I do want to talk about it, but I do not want to encourage you to use sequential function charts because they have their limitations. The limitations of this is this, that while you're doing one thing over in one area, you're forgetting about all the other areas. And if you don't consider them at the same time, many times you have an issue, and that issue is one of I forgot about the safety aspect while this is going on. So you're forgetting about the safety when you're in another state. You don't want that. You want safety on all the time. And so this language was popular back in the 90s, and a company called April was the first to really come up with it, and they called it GraphSet. And they had an area called P0 that for whatever reason, if you were not in one particular state or another, you use P0 as the area that was just the catch-all. So I asked a guy who had been programming in this, I said, how much of your program actually ends up in this area called P0? He said about 90%. So if your language is only good for maybe 10% of the application, and 90% is generic and is going on for the whole system, then it may not be the language that you want. That said, I'm going to show you an example with this language. Okay, so this gives you a little bit of an idea that SFC is a language. It's not one of the ones that we talk about in this course. It's not one of the ones that's supported by your programming language, but it can be added. It's a separate language that can be added to the PLC, and some people actually do use it. Okay? So here is an example of sequential function charts. So in this case, we start, and then you have a choice. You can either go down this branch, you could go down this branch, you can go down this branch. Now, if you go down this branch, the logic in these two branches does not execute. It's just the logic in this branch. So you can see what I'm talking about here with this idea of safety. If there's some safety tied in with this one, safety tied in with this one, that you didn't catch over here, you might inadvertently have forgotten about it when you're in this branch. It has to be in all three branches, or else it isn't going to work, or you're going to set your safety issue is going to come out and get you. And I have an example of that, and I'm going to tell you right off that it is a little bit graphic, but on the other hand, I think you probably, if not appreciate it, at least understand what I'm trying to say. So my dad he's passed away a few years ago, but his adult life, he was a farmer. And I grew up on the farm, and basically that's what he did. And when he told me more than once, but basically he told me how he would go out about killing a groundhog. And groundhogs were not your friend. They would eat up beans like crazy. And typically a groundhog could clear off a couple of acres of beans by themselves. So one groundhog was deadly, and you'd want to get rid of him if you could. But he would never take a gun with him on his tractor or anything like that. But he said if you saw one out in the field, he said you can outrun them. I didn't know that, but he said you could, and I believe him. But he said they'll turn and defend themselves, and they'll rear up, and they'll try to not attack you, but at least defend themselves. So he said what he would do is, to try to get rid of them, would be to take two long wrenches, like two pipe wrenches or whatever, maybe a couple foot long each, and so he would tease them with the one and get them to be their attention on the one, and then they would be fighting with this one, and all of a sudden with the other one he would club them, and that would be the end of Mr. Groundhog. So the point is this. It's graphical, but you've got to take care of all angles. You've got to watch all situations all the time. And in this situation, while you're over here thinking about this one, you've also got to account for any possibilities that might happen in any of these. So you really want to take all your safety and put it in some generic place outside of these, and then you have a better chance of making your system foolproof and not having accidents like you could if you just were thinking about one thing only and not the others. So again, most of your safety aspects should be done across the board and not in any specific one of these boxes. Okay, so this would be one where you could actually have multiple ones going on at the same time, simultaneous branches. And also here is one where you step, and subdividing of actions and doing things in sub-steps. So again, SFC, it's a language, you can use it, and I actually have an example of it here in a little bit, and I'm going to show that to you. But first of all, we want to talk about other names and other things that you might have heard about. So one of them is the initial FSM, which stands for finite state machines, and you may have heard about this as a topic in the development of digital computers, and you might have heard about this name. So I quoted it, and I just wanted to let you know that that's something that is similar to state diagrams, and you can use these kind of in parallel with state diagrams, but it's the same basic thing. We're talking the same language when we're talking state diagrams as we're talking about finite state machines. Same thing. And also the idea of a Petri net. So if you wanted to take the idea of state machines and move it to a very high level of math, you could. And if you want to get your PhD, you may not be able to get a PhD today, but at least a master's degree in electrical engineering by using Petri nets to solve a problem. And Petri nets basically use transition from state to state based on a matrix manipulation. So basically they use numbers, and they use multiple equations and multiple variables. So basically this would be a high-level math equivalent to are state diagrams. So let's get back to reality. How do you know many times whether or not you're needing state diagrams? Well, the rule of thumb is this. If you come to a point where you think you need a switch for something in your logic, but you don't have that switch, and there's none provided. But you need to know, do I go left or do I go right? What do I do? And that's sort of a situation, all of a sudden you say, this is a state diagram program. Why? Because you're being asked to set some kind of a circuit for that. In other words, I'm either going to do this or I'm going to do that. And when you are in that position, when you need a switch but you don't have a switch, start thinking, this is a state diagram program. I need to start making memory circuits that would go from step to step to step. And sometimes you talk about like a lily pad. If a frog is wanting to go across a pond and he doesn't want to get his butt wet, so he looks out there and he sees a lily pad, so he jumps from where he's at to the first lily pad. Then he goes to the next lily pad. Then he goes to the next lily pad. Then he goes to the next lily pad, and he finally gets across the pond without ever getting his butt wet. And that's kind of crude again, but it does give you the idea of going from step to step to step to step to step, making decisions about which way I'm going to go. And many times you have switches in your program for a specific reason, and they're there. But sometimes you come up to this, I don't have a switch. And when you don't have a switch, you create a memory circuit, and then you start thinking about, well, what does it take to get to this memory step? What does it take to get to the next memory step? What does it take to get from step to step to step? And that's where state diagrams really do become powerful, in that you can now start drawing these circles and saying, I go from step to step to step, and that's what the lily pad or the circle is about, and you draw the arrows and you go from step to step to step. Okay, so need a switch, don't have a switch, think state diagram. And again, sometimes state diagrams are developed by using scan, and I give an example here of what we call climbing the ladder. And this is a case in point where you have 3 conveyors, and you say, I'm going to run these conveyors, and then your boss comes along and says, no, I want you to be able to add a master stop and stop them all. And then I also want you to punch one button that says restart the ones that were running when you stopped. So again, you have these states, and you realize, that's a state diagram. It is. But it's also using of scan, and this explains just how you can do that. And you can do that and actually create states. And I'm going to show you that right here. So you push the button to stop, and you go off, but when you push the restart, you're ready to turn back on, or you push the stop and you're back in the off position. So basically, it allows you to define multiple states by using just ahead of what you previously had done using the scan of your programmable controller. So I arranged my logic so that just prior to the scan, I have something that happened, and then I go through and do the next thing, and then I can do the next thing, and do the next thing, and do the next thing. So here is a use of scan of the programmable controller to build these states that allow me to do something that otherwise would have seemed hard to have done. It's not hard if you use the scan of the programmable controller many times to build simple state diagrams. You say, what did he just say? Believe me, if you get into problems like this, please come back and review this kind of thing, because it helps to say, okay, he got me at scan. Well, the scan of the program is important, that you set logic in an order. Well, here you're setting the logic, and then you're using that for future statements, and then you're coming back and you're remembering certain things, and you're using it as you flow through the logic again and again and again. You say, would this ever work with relays? No, it never would, but this is something that you use the cyclical nature of the scan to actually be able to set various states in your program. And that's all I'm trying to say. You say, well, it's a trick. No, it's the use of scan to make your states. So again, I wouldn't worry about this as an example. It's not something we're going to test you on, but it's something that as you look at state diagrams, you probably will say many times simple ones can be solved just using the scan of the programmable controller. And that's true, it can. Okay, I know that's an aside. Now, three conveyors. Three conveyors. Right here we have three conveyors. And again, would we use a state diagram for this? Probably not. Typical conveyor programs do not need state diagrams, but if you did, this would be one way of doing it. So again, you have arrows and you have circles and you go from state to state to state, and you can see that it might be of help, but I would not say this is something that I would ever draw before I started programming. But you can. You say, why are you telling us so many that don't? Because I want to emphasize the idea that this is an optional thing. Sometimes it helps you, sometimes it doesn't. If it helps you, it can really help you. Here's an example that really does help. This is called the electronic safe. So what do you do with this electronic safe? Well, you key in a number. You type in on this keyboard a 3-digit number, and you display those 3 digits. Then you click next. Then you click in 3 more digits, and you click next again, and you do 3 more digits. Then you click, after you've done it the 3 digits 3 times, you click open, and if you've done the 9 digits in the correct order, it'll open. Otherwise, it won't. So how do you do that? Well, here you see it right here. Enter the first digit. Enter the second digit, enter the third digit, hit next. In other words, if you don't get these right, you ain't getting it. But again, you take all those information in. When you push open, if all 9 digits are correct, you have success and you open the cylinder. Otherwise, you don't, and you go back up here and you start over again. You basically go back to 0. So you see what it does. It collects all the information, and then you push the word open, and then it either decides to give you a success or failure. Okay, what else? What does this remind you of? How about your garage door? Your opener and your garage door. Same thing, only it's not 9 digits, it's just 4. But it's the same thing. It does the same job. And it does the same actual, it opens or whatever. Now this is something from a factory. How many cylinders do we see here? Let's count them. We've got a cylinder right here. This is a cylinder. We've got a cylinder that goes down like this. We've got a cylinder that goes over like this. Okay, so how many cylinders are there? 3. So, can we do this easily? Yes, we can. We can have 3 cylinder state diagrams, or we can combine them. And we also have the idea of manual, homing, and automatic. Which one would we concentrate on? Concentrate on the automatic. But we also have this idea of how do you home something, and also how do you make this thing operate in manual. So you worry about these as 3 separate issues. You worry about them in the automatic mode, you worry about it in the homing mode, and you worry about it in the manual mode. You don't mix the 3. You think, I'm in this mode, I'm going to do this operation. I'm in this mode, I want to do this operation. I'm in this mode, I want to do this operation. You have to concentrate on the specific mode you're in order to get this thing to work. So here's one of the cylinders, the 4 states. Here's another one, the 4 states. Here's another one, the 4 states. Okay. So is that as far as we have to go? Well, in this case, we're going to actually show you an application using, believe it or not, the SFC, sequential function charts. Now this is the sequential function chart for that application in automatic mode. Okay. Say, well, you just said SFC isn't the way to go, but here it kind of mimics the state diagram approach, and it kind of works. I don't deny that you can see the idea of you go down this, to do this, to this, to this, go up here, do this, to this, to this, to this, and you're done. This is the automatic state. Okay? These aren't circles, these are squares, but basically they do the same thing. And at each state, when it satisfies these certain things, then it goes to the next state. So it satisfies this, it goes to the next state. Satisfies this, goes to the next state. Satisfies next, it goes to the next state. Okay. So it shows the steps and gives the sequence of flow. All right? So this would be a way of defining that with the idea. This is the homing diagram. So this is the homing mode right here. So this would be an example of the homing mode for those 3 cylinders was right here. This would be just the homing mode state diagrams. And this is these are 3 diagrams, or these are 2 diagrams that I took from a project or a school that when I was in Germany. And basically this is an example of state diagrams, and the way that the Germans show the state diagrams is right here. And this is very good because this shows you the condition that allows you to go from this state to this state, and this sets what is in that state, and then this allows you to go to the next state. That's what's in this state, and it allows you to go to this, and it continues around, and arrows show you what it takes to go from state to state to state. Now, very rarely do I put all these conditions in here. It's kind of like it's too complicated to do that on the state diagram, but I at least allow you to see the state to state, and then what's going on in that state. Where are you at, and what's going on in that state? What is that state? What does that state mean to you? So that's the homing mode, and this is the an alternative state preventing the drop down of parts from the memory. So again, this is an alternative to this one, and I just wanted to show these to you because they do give you an idea as to the complexity of state diagrams if you so choose to do that. Now, this is very complicated, and there's a lot to this, but if you want to, you can describe the whole thing with these various state diagrams. See, are you going to ask me to do that? And the answer is no, I'm not going to ask you to do that. I'm just going to tell you that you can get rather complicated, and that's a situation where you can actually get into. All right, so this would be a definition of a state diagram. So you have these bubbles or circles with state names, and then you have transitions and what you can do to get from one to the other. And these are conditions listed. So this is a definition of a state diagram. Here's a state diagram, or here's a single pneumatic cylinder. And it does a specific job. This is a riveter, and it comes down and bangs down on this metal, and then it goes right back up. Now, in a question like this is, how many states are there in this project? You said, well, cylinder, single cylinder, 4 states. And I want to say to you, yeah, there could be 4 states, but there didn't have to be. In this case, this being down is only for about 1/10 of a second, and it starts moving right back up. There's no reason to have the down as a state because it never stays there. It goes, and you can easily describe this in 3 states as opposed to 4. It's your choice. Which is right? I don't care. They're both right. The answer is both. Both are right. Why would you use this? It's a little simpler. So only do not use time delays as a state. So if it's just a time delay, don't use it as a state. Okay, so now how do I define, if I have cylinders in a project, how do I come up with a state diagram? Good question. You can either come up with multiple state diagrams, or you can combine them into a single state diagram. Now look at this. This is again from the Germans, but look how they did this. Here's one state, and here's one cylinder, here's another cylinder. So, which is better? 2 state diagrams like this, or 1 state diagram like this? Well, they argue that these are better, that this is the best way to go. I argue that this is the best way to go. This is typically called a runoff diagram. These are with separate cylinders, and this is a runoff diagram. This is a combining of everything. I like this because this is how you program things. This is how you would do things in normal. You would go from state to state to state to state to state, program those, you're done. You don't program these, you program these. So that's why I like this better. And if you can see this, you're better off than if you have to program using these. This is hard for people to see. This is easy for people to see. Use the one above, if you can. And that's what I'm suggesting you do. So what are you being paid to do? You're being paid to write computer programs, PLC programs, that control a process, right? Instead of trying to be theoretical, you're trying to write something that is having to do with reality. So has anybody ever paid you to write a runoff of, like, this is the condenser that they had up above? That's a state diagram for the condenser. What is it? It's a bunch of steps, isn't it? I'm filling, I'm half full, I'm doing my condensate. No, I'm doing my condensate and condensating complete, and then I come around here to my start position and I fill, and then I go from there. Okay, so I think this is I think it's actually backwards. I'm full, and then I'm half full. So they got these two backwards. But anyway, you get the idea. So there is an instruction in Allen Bradley that is not in Siemens, as far as I know. I've never seen it. It's called a sequencer. And we're going to talk a little bit about how to write sequential programs. Now, this would be an example of something you can use sequential programming with. This is a robotic arm. This would be an arm that would be down, and then you can raise it up like this, and then it can be rotated around 90 degrees. And you could pick up an egg or something with it, and then you could rotate it back and then set it back down and then drop off the egg. So that would be a state diagram of sorts. It's also a sequencer. What are sequencers like? Well, sequencers are like this. They are devices that are that they go around in a circle in one direction, and they don't come back. They can't go backwards. They're sort of like everybody's used a ratcheting wrench. They're sort of like a ratcheting wrench, and they only go in one direction, and then they go back to their home position, and they're done. So basically, go step to step to step to step to step to step to step like that. That's a sequencer. Or you can use the sequencer idea for that. Now, there is a sequencer instruction, but I do not like using those instructions because, and I'll give you some examples in a minute. But how would you write these programs? Okay. Well, they're basically written based on the following. You start with a what we call a permissive string to get you started, and then when that goes, you push the start button, initialize right here, and excuse me, this is the button you'd say to start, and then you would set this coil. Then you do the first step. Okay, when the first step is done, you realize that these would turn on, and then this one would turn on. So basically what happens is this one turns on, then you're doing step 1. This one turns on, then you're doing step 2. This one turns on, and you're doing step 3. This one turns on, and you're doing step 4. So what happens is seal, 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 done. When you're done, the last one turns them all off, and you start over again. But you see how you turn these on in sequence. Now, what is good about this kind of programming? Well, it's good for the idea that you can use this, and you can have a programmer, or you can have an electrician use these, and they'll get the idea, and they will like this kind of programming. What's bad about this kind of programming? Well, if you have a very complicated process and you have to tear it apart and put it back together 3 or 4 times, these get messy. So my recommendation is, if you have more than a few steps, maybe 5 to 10 steps, if you go more than 5 to 10 steps, use numbers. Use a number to save what step you're in, and this would be where you would store that number. This would be a location for that number. Okay, this would be the location for that number. So if you have a really simple stepping program, use ladder. If it gets very complicated, use numbers. And that's my advice to you in general about these sequencer programs. Each step you go, you add a number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Done. What if you have to add some steps? Well, you can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 13, 14, 15, 16, 17, 18, 19, and then 10, 11, 12, and done. And that works. And I've done that. You don't have to go in order. Okay? how do you add time between steps? You had a timer in the circuit. So basically, this sets the step, and then you go to the next step. So that you would write the steps above, but you would actually put the timer in, and this gives you the time delay between steps. And that would be with numbers. Okay. There are instructions called sequencer instructions. They're called the SQx instructions. Sequencer output, sequencer load, and sequencer control. And in RS Logic 500, there are these, and with RS Logic 5000, these instructions. So why did some companies provide these instructions and other companies didn't? Because they basically, these instructions were meant to mimic the old style drum switch. The drum switch was a switch that was used to set bits as you went through various steps, and that would be like this kind of thing where you're actually setting a bunch of bits in steps. So if I had these outputs turned on in step 1, I would turn those on. This is hard because unless you're the person that's setting that up and you have good documentation and that the documentation is passed along, people that pick up your program later on don't have this chart, don't have the information that you had, and as a result, it's very hard for somebody after the fact to come in and diagnose what you're trying to do. So sequential instructions, SQx instructions, are useful only if you have a large number of inputs and outputs, and if there's something that you have some documentation on, or if you were the person that created it. It's useful in that situation, but otherwise use the steps using numbers. And that's my advice. Okay. Now, this is an application that was actually done, and it was built, and I'm glad that I did it the way that I did it, because in essence it allowed me to not basically have to worry about starting up this process, because the guy that looked at my state diagram got it, and he started my system up for me, and it worked. So basically, anytime you have something that is that works that well, you say, wow, that was good. So basically, what it was being able to see that this process, which I'm going to talk to you about here for a minute, was a state diagram. It qualified for state diagram, and it worked very, 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 very well. So it was a reheat furnace for a steel system where they made rebar. And so they took the steel bars, which were billets, and they were like a Lincoln log, but they were like 20-foot long Lincoln logs, and they were 5-inch square on the end, or they were 6-inch square on the end. So basically, these were big pieces of steel. And they would lay them on a table using an overhead crane and an electromagnet, and then these billets would move down, and they would move down to a transfer table, 2 of them, and then they would get transferred over to another table, which would be a charging table. So basically, you would drop the billets on this table, they would move down to here, and at some point in time, they would come over to this charging table. So how did that all work? Well, it worked based on what? State diagrams. And these state diagrams are tied together. So it wasn't hard once you saw the idea, but this transfers, you start the billet on this one, and it would move to a certain position, and then this state diagram would sync with the next state diagram. So where you were in this state, you could transfer billets over to this table. So here would be where we could actually transfer, and this one would have to be in this state, this one would have to be in this state, and then we could transfer over. And you say, well, how did that all work? Well, this was at the discharge end. The discharge end had to allow enough space to actually add more in. So you had to take some out before you could put some in. That's typical of how processes work. So basically, we had to discharge, and the discharge had to meet where you could accept billets with where the charging furnace could actually move billets in. So if you see this and you can accept the idea that this is a little made up because I didn't want to give away the exact methodology that I used, but it's the same basic ideas. I used a state diagram linked to another state diagram linked to another state diagram, and this state had to be the state to allow pieces in. This was the one that allowed pieces out, and that's how it worked. So again, I want you to understand that different state diagrams can be used for different applications, but this one, I didn't even have to show this diagram to the engineer who was doing the checkout, but I did, and he understood it because he saw it in the programming. And I used numbers. So again, step, 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 a certain step for this one, allowed a step to come in for this one. It worked. And as a result, I didn't have to go back for the startup for that part of it at all. And you say, well, when was this? This was in 05, and this was a process that we did and programmed, and it worked very, 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 very well. So a billet state diagram, it worked. So if you ever hear of the word billet, you'll say, oh, that must be a state diagram program. May or may not work, but again, and you say, well, did the people that built the original furnace have this in mind? I think they possibly did, but it didn't really matter because I saw the state diagrams as a result of looking at the equipment, looking at how the equipment had been designed to work, and I designed the state diagram based on how the equipment was designed to work. And then I put it in. I put the program together based on the state diagram. The program functioned flawlessly, and I'll say this, it was, if I hadn't seen the state diagram, it would have probably been a lot harder. So seeing the state diagram made the programming of the process much, much, much easier. That's the goal. Okay, so this was the getting the pieces out, how do you get pieces out, and we talked about that a little bit as well. And I'm just going to talk about the idea of this is just a little bit of the help of like a subroutine, that type of thing. Okay, so anytime you see a sequential set of events, this to this to this to this the flow of the events. Think state diagram. And if you're sitting in a parking lot trying to get out from a movie that you saw or a show that you saw at a theater someplace, and you're sitting there and you move up position to position to position as you're trying to get out, say, this is a state diagram. This is where we're at in state diagrams. And that's exactly the truth. I programmed a project for Libby owns Ford quite a few years ago now, but anyway, the fellow that had been doing the project had kind of thrown his he kind of threw things away and kind of just left. But what he was trying to do was to add a state to a line, okay? And the original programmer, I could pretty well figure out what he had done. He had put step, 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 and then when you get to a certain step on this one, you can go to the next one and you can transfer. So the pieces of glass were the same as these cars, and you would move, when this one moved, this one could move up, this one could move up, this one could move up, this one could move up. And what they wanted to do was to add another station there. They wanted to like split this car in half, but basically they wanted to have two steps where there, or two states where there, or two stations where they just had one before. So I looked at it and I said, well, if you initialize with getting another car in this position, in other words, two cars in this position instead of one, everything from that point on would just work. And I tried it and it worked. I went and asked the electricians and I said, have you ever seen this thing work that way? And he said, oh yeah, every once in a while it skips and gets into that mode on its own. I said, thank you. So I went back and wrote a little program that would, if there wasn't like this half a car wasn't there, I would make sure that I would run this one halfway, and then I would have a half a car here and half a car here, and then everything else would run. So I would initialize, and from that point on the program ran automatically without me having to rewrite anything, and it worked, and they were happy. And if you can see programming as state to state to state, that works very, 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 very well in most applications. If somebody wrote that, whether they realized it or not, that's what they were doing. So again, if you can see that, it always helps to be able to see how that fits together. Whether they use numbers or not, Hopefully they did. If you get into a situation like this and they used coils, all coils, it's a pain. But you don't have to go back and rewrite it. It's just realize that, oh, at this step, this meshes up with this one, and then this one can go on, or whatever. But please be aware of the fact that whether they realized it or not, they were writing state diagrams, and that's pretty much how you can address certain programs. Okay? Going back into other people's programs is extremely difficult, and if you can look at the process and figure it out that way, many times it helps a lot. Again, this would be a moving of parts from station to station, and that would be like the ability to move from state to state, that type of thing. Okay, we've talked about timing of states. Troubleshooting. How do you know when something happened or not? Well, one of the best things you can actually put is a counter. Even though some things you would see maybe as one-shots, you don't know if they happened or not, use a counter. Counter is your best friend. And also, we talked about earlier, last coil wins. You remember I talked to you about this one would dominate the other two. But if you do something like this, if you take this to here, and then these, and then this to here, and then do these, what have you actually done? You've done this, haven't you? And believe it or not, people do this. And believe it or not, that's why they let you do this, because they know that you can feed here to here, here to here, and then this is actually the compilation of all this. You say, well, that's not fair. Somebody ought to take that away from them. Well, at times, this is a very useful concept, and you want to be able to accomplish this. So now we've let you open the box and say, I see why they don't block you from doing this last coil wins. Every once in a while, it is for your benefit. So that gives you the idea of why last coil wins is actually beneficial. So we've drifted a little bit at times talking about state diagrams. We've talked about scan, and we've talked about last coil wins, and we've talked about groundhogs. But there is a very good reason for state diagrams, and their usefulness to your programming, it cannot be minimized. We don't have a lot of labs for this. We do have some things you can think about, but basically these get very hard very quickly. The sequential program where I talked about using relays, that's probably going to be one of your first programs that you would use. Maybe, maybe not, but I want you to at least remember that when you get a job, they're going to test you, see how you do. And one of the first things they probably will ask you is to write a little sequential program that they probably could knock out in 2 hours. It may take you 2 days, but at least you can recognize it as a sequential program, a state diagram program, hopefully, and be able to knock it out, not in 2 weeks, but maybe in 2 days. And they'll say, well, you probably are worth keeping. And that's probably one of the first things that they'll do is to say, we got this little program over here and see how you do. They're not going to let you go, but some of their initial how you do what you do is going to be based on some of this kind of things. So again, we don't have a lot of applications that we can do to prepare you for that kind of thing, but I can tell you that that's a possibility that you will have to do, and they think those are simple programs. They are once you've been programming for a while, but they're not easy. And if you look at them and you say it's going to take a little while, it probably will. But please be aware of the fact that they may throw you that curveball and see how you do. Okay, so this is a sequencer. What is it? It's a timer you put on your Christmas tree, isn't it? What's the deal? Well, you set these bits right here. This is a bit. It's either on or off. It's a switch, right? At a certain time, you're either going to be on or off. And that's a rotating thing that goes 24 hours, and it comes back around, and you do it again. But that's a sequencer. Whether you realize it or not, there it is. You can program that too, can't you? It's a fairly simple device, but you can program it. Okay, so this chapter is about state diagrams and their little cousin, the sequencer. Both these tools are useful in programming difficult machine operations and allow the programmer to walk away after an installation with the satisfaction that the operation of the machine has been developed logically and the maintenance of the machine will be easier if developed otherwise. A common statement from many end users who depend on others to program their processes is they don't want spaghetti code. This is a metaphor for difficult to diagnose code. We have all seen others' code that we would term spaghetti code and wonder who would ever create such a mess. We would remember that we need to look at the end product from the consumer's point of view and give the best effort to create a program that both works and is maintainable. Okay, so I mentioned the KISS method before. And I was asked once upon a time if I knew about the KISS method. And I kind of looked at the guy and I said, "You're telling me that I've gone overboard." And he was right. I had gone too far and I had to back up and make it a little simpler. So the last letter of that word is the one that you don't want to have happen. So again, remember the KISS method, always remember it, and make your processes simple and understandable and hopefully expressible with a state diagram if possible. Sometimes you don't need them, but sometimes you do. Okay. And as I said before, the boss will try you out on something simple, maybe like these programs. It is a test. So if you're to pass this initial test, you should be able to see the problem as a simple sequence and develop the program appropriately. This is a strong motivator for you to understand the concepts, at least to a point, for how to develop a sequential program or state diagram program. Hopefully you will be able to move quickly through this initial test and onto more meaningful programs down the road. Again, no scare, just wanted to tell you that that's probably one of the things you'll probably end up doing. Good morning. This is the second part of the Chapter 11, and we're going to go through the exercises and we're going to talk about the lab. We're going to give you some hints on the lab. So basically, we're going to go through and then I'm going to work on some of these exercises at the end of Chapter 11. And I'm going to tell you up front that some of these exercises are rather laborious and long, and I'm not going to even attempt to go through some of them. But just to introduce you to them, and when I went to the Germany experience in 2008, I came back and had some of these labs that were from there, and this was one of them. And it was a machine that actually was an elevator, had a motor at the top, and basically it had a cage that you could lift up. And the stories were the base floor, which was basically floor one. That would be your walk-in. That would be your ground floor. And floor one is in Germany the second floor. That's one above the first floor. And this would be two above. That would be the third floor. And that would be the fourth floor. Don't be confused. They're based on zeros. So basically the number of their floors differently in Germany, but that's okay. And we're going to talk about some state diagrams for this process. So we're going to talk about that a little bit. We're going to talk about a little bit about this one, which is a fairly easy one, but we'll talk about it. And then we get into some of these. These are machines that were actually at the facility there in Germany, and just a town just a little bit out of Stuttgart, outside of Stuttgart. And these are Festo machines, and you probably would wonder, well, why don't we have Festo in our labs? Well, these are very good labs, by the way, and they take a lot of time. These would be like capstone labs, but they were labs that were provided and basically would have to be wired up and then programmed, and these would be capstone type labs. So there were a number of these labs, and I basically and their Festo has moved on, and they have newer versions, and they have these tabletop labs. We do not have any of these labs in our facility. That doesn't mean that it's not a good idea, but they're expensive, and we basically do not have that. We just don't do these. But that being said, this is only one style of programming that you would use the state diagrams specifically for this this program, and it really begs to be using the state diagrams. But this is only one type of programming. So if you would dedicate all your put all your eggs in this basket, it might be useful, but yet it's just one chapter and it's only one part of what we try to cover in the overall text. That said, these are very fantastic labs. So just imagine you were there and think about how you do a state diagram for a machine like this. And this is a pictorial of it, and then the graphic of it. And I actually ask you if you want to give it a shot, and you give it a shot to any of these. This is another one, similar. Now this one is not. This is a fairly simple one, and it would be basically, we'll talk through this one. This is the Simon Says program, which is in chapter 13. This is another one of the Festo labs, rather simple, but yet, and then we basically, this is a problem that I actually ask in a test. Ones that some of these are asked that I've asked in a test, but basically this is going back and looking at this project and this chapter, and it asks you to come up with an I/O list. So basically, let's find the inputs, find the outputs, and that would be all we would do there. And this one is a sanding operation, and it goes down and it travels back and forth, and it passes this. There's a part here, and it goes by and sands it 5 times, and it goes in the same direction and sands it each time. So I want to come up with a diagram for this, if possible, and to talk through how to do a state diagram for something like this would be, it's very doable, and I want to talk to you about how the state diagram for something like this is very doable. I want to talk to you about that. And last but not least is the 3 pumps. This program is a program that I ran into as a employee of Owens Corning Fiberglass, and I basically was asked to help another fellow, and it took my breath away, first of all, because this is not an easy project. Now, it's easy as long as you are only in automatic and everything is running in automatic. It's fairly straightforward because you basically, in that mode, you just basically follow which one was the last one turn on, and the next you just turn on the next, turn on the next, and it's a rotating cycle of turning on the next one and then turning off the one that was the furthest back. In other words, the one that would be the one that had been on the longest. But if you mix auto and manual and have the ability to take 1 or 2 or 3 of these pumps out of the auto sequence and put it in manual, this project becomes a lot harder. And that's why I'm asking you to do this one, because this is just a lot of logic. And sometimes you can look at a program and immediately have a solution. This one is one where that's not necessarily true. You can just start, and you just have to start, and then you think about concentrating on one pump, what it would take to turn on that pump, and then all the things that would turn on that pump, and then all the things that would turn off that pump, and then an auto and then manual, and you would have to ask all those questions in order to solve this problem. So basically, this is just a long problem. This is not a easy problem if you go through and do it with the auto and manual options, and that's pretty much why I ask you to do this, because this is one of those projects that it's not necessarily a state diagram, although it does use the idea of the scan and working through the scan, and I'll explain that in a little bit. But basically, this is a interesting problem, and it kind of uses state diagrams, although we don't actually draw the state diagrams, but it does help you to, if you have the idea of state diagrams in mind. So anyway, we talk a little bit about this part of it and the state diagrams, and then we also talk about it if you had 4 fans instead of 3 pumps. And when I was presented with this program, I actually did have 4 fans. I had both. I had 3 pumps and I had 4 fans, and I had to put them both together, and both programs had to work, and it was fun. But anyway, we'll let you look at that in a minute. So let's go back and start some of these projects and see where we're at. So we have a white screen now in front of us, and we're going to go through this, and we're going to start working on some of these problems. Okay, so problem number 1 at the end of the chapter is on the elevator. So problem number 1 is on the elevator. We want to do a state diagram, if possible, for that. And hopefully you have a copy of it in front of you, as well as looking at my suggestions here. And if you look at it for a second, you think, what basically is the philosophy of this process? What's the philosophy? Or the base rules for this elevator? Well, you have to think about it like this, and then everything is an offset of this. Either you're going up, you're going down, or you're an idle. Okay? So if you are going up, if there's a request to go up, you go up until all the up requests have been satisfied. Then if in the meantime, if there's a down request, you go over here and you meet your down requests. You go down. If there are no requests, you go back to the idle or the middle position. So basically, if you can see these 3 basic states and then start building on them, you can build the sequence for the elevator state diagrams. So you can build all the parts and pieces based on these 3. So you would say, I'm going up and I'm at this point, but I'm going up and I'm in the, I just hit the limit switch and I'm going up, and I'm going to stop at that floor. There's a request to stop at that floor, and I hit the limit switch just prior to that floor. So basically, you have at each floor you have 3 limit switches, one just above, one right at, and one right below. So if you're coming up and you hit that one just below it, and you're going to stop at this point, and you're in the up mode, you see you go to another state. So at this point, when you hit that limit switch, you go to a slow or like a dribble state, and then you stop at this point. You stop at this point, then you do the opening of the door, which is part, and that's another part of the state. Another state, you open the door, you let the person out, and then you close the door, and then you proceed to the next one, as long as you're in the up mode. Okay? So if you're in an up mode, you're going up, doing things to get people up. If you're in a down mode, you're going down, and if you don't have either one, then you have to decide what you're going to do about idle. Now, does idle mean you go to a specific floor and wait, or does idle mean you just go to the floor you're at and wait? That's up to you. That's a question mark that you have to decide. So, I didn't do all the state diagrams for you, but I think I gave you a beginning of how to do the state diagrams for this program. And in other words, you could program this from right here. You could set it up and program it, but you really do need to identify all these states, and I think that's something that you probably would do. You don't have to, but it would be advisable to do all these intermediate states, these smaller states, as opposed to just these 3. But these 3 kind of crack the whole program wide open, and everything else is a subset of these 3. So I think that gives you a little bit of an idea how to do this one. Not that we've solved everything, but we've at least gotten to a point where you I think can go ahead and solve it. Okay, so problem number 2 with the elevator. So with the 3 levels, so you basically have a start position. Okay, so you have an init, then you go to when you push the button, you start. So you push the button and you start. This would be the step 1. And when you're in step 1, you're filling to the first level. Then you get to that level, then you go to step 2, and you can write them outside if you want to instead of inside. Then you do step 2, and then you do step 3, then you do fill 3, and then you're done. So this is a very simple one. By the way, this is kind of like the sequencer logic that we had before, but I wanted to remind you of one thing with sequencer logic, and I did not mention it earlier on. When you have step to step to step to step to step and then done, like we did for the sequencer logic, if somebody comes in here and stops it at that point, and you're doing a step, and they stop it, for whatever reason they do that stopping, you have to be careful about how you reinitialize, because for what it's worth, I was working on a press. It was a pneumatic press, and this would be the visual of the press. It was a hood liner press, and here was a light curtain. Okay, so we had a light curtain, and here's my buttons that I pushed to say start. So I pushed these 2 buttons, and this press came down. Now I was going to look at something in here, and I wanted to check it out, so I walked into the light curtain, and it stopped the press. But then I walked inside the light curtain just right here, and guess what happened? It took off on me, and the next thing happened with the press, which is something you don't want to have happen, because you want me to have to come back out here and have to start the buttons again in order to reinitialize it. So many times you have to ask the question, if there is a process stop, how do you restart? And this was not a good thing for me, and I immediately went back and I put that back in I put that in the logic to allow that to only happen. Now in today, if I were to do that today, I would do this with a safety PLC. But that doesn't help me either if I don't write the right logic. So I'm convinced that even though you might write with safety logic, you still have to prepare for the idea of if you're going through a sequence of events, that you still have to come back out and remember to do all this other stuff as well. So having a safety PLC is helpful, and it gives you a level of safety, but you still have to write the logic correctly in order to get it to fully run. So that's a question. This would be number 2, and this would be just a thought for that as well. Okay. Problem number 3 and problem number 4, I'm not going to do. If you are interested in working on these with state diagrams, I would be interested in helping you. But basically, you have modes, you have auto, you have manual, and you have home. And you have to write state diagrams for all 3 of these. So if you are interested in doing that, these take time. These are not easy labs to do, but you could spend quite a little bit of time writing the state diagram for the auto mode, the state diagram for the manual mode, the state diagram for the homing mode for either number 3 or number 4, and that would take quite a little bit of time, but it can be done. Okay, so number 5. So you have these bubbles, and basically this would be not playing. That'd be number 1. Number 2 is playing, showing the lights. Playing, showing the lights. Problem number 3 is playing and allowing them to push the buttons. And number 4 is you won and flash the lights. So this would be the answers to number 5. Fairly straightforward. Number 6. So with number 6, we're asking for you to identify the from this is a drawing of a sequential function chart, which is like a state diagram. How do you find the inputs and the outputs? Well, the inputs are these things called these I's. Okay, so the input list are things like I underscore B 3.2 part in pick position, and I underscore B 3.1 separator back. You get the idea. Part at gripper. Y is up. Y is left. Y is up. Y is right. So those are your inputs. Now, what are your outputs? Separator fourth. This would be something that you would tie to a Q or an output. Separator back. This would be, now, depending on the type of cylinder that you have, if it's a dual cylinder, you would turn on an output for the one until the limit switch is made. Then you would turn that one off and you would turn on another output for this one. Or you would turn this one on and then turn it off and it would come back. If it has a spring in it, it would just come back. So it depends on the type of cylinder that you have. But these are potential outputs. Y down, Y up are two outputs. X left and X right. Again, depends on the type of output that you have. So that gives you a list, potential list at least, of which output goes with which one, and you're certainly capable of seeing that depending on the type of output, it could either be one or two outputs here. Okay. So now we have a number 7. We have a machine that goes back and forth, and it goes back and forth 5 times. So we can write this as a subroutine if we want to and make the subroutine act 5 times, or we can use numbers. It's up to you. I like numbers because it gives me the opportunity. Well, it's makes it fairly straightforward. But so when you push the button, you go from 0 to 1. So basically, when you push the button, you go from 0 to 1, and that would put me in state 1, which would be I'm moving to the right. Okay, and I move to the right until I see PE2, and at that point in time, I'm in the sanding mode. Okay, so CPE2, sand. Turn on the sander. I do that until I get to PE3. At that point, I stop. Okay, so when you get to the stop, usually I say you don't use the stop as a state, but in this case it's your choice. So you may want to add the stop as a state and have a timer there. So you basically time, and then you start back to the, okay, so this is moving to the right, and then this is moving to the left. Okay, so you move to the left. So this would be state 3, and then you move back to PE1, and that would be you're moving to the left, and then you're stop in time, and then you're moving to the left, and then you hit photo I1, and that puts you at step 4. Okay, so now I am in step 4, which is kind of like step 1. It's kind of ready for step 1, but again, I can go back here and I can say, okay, now I can just repeat this with step 5. Step 5 is like step 1. Step 6 is like step 2. Step 7 is like step 3. And step 8 is like step 4. So I can do that. Now this is my second pass through, then my third pass, my fourth pass, my fifth pass, and then I'm done. So the last thing over here would be a coil called done. So that's one way of doing this. Is it the only way of doing it? No, but it works. This is a kind of one way of doing this step, this sanding, and I would recommend this as a possible state drawing for this problem. Okay, so now we go to the pump project. So in the pump project, I give you hints on the pump project. So the lab for the 3 pumps, you have a button for more and you have a button for less. So I want you to make those one shots, and so this would be my more one shot. This would be my less one shot. So now I want to put this into a bunch of rules. Okay, so rules for starting that would say, okay, this would be everything. It would start pump 1. The rules for stopping pump 1. Okay, so obviously the more and the leading edge of the more, and the rules for if this then that, if this and that, and in other words, but you need to know more information. You need to know who was on last, and that's other information that you have to develop later on, and I show that in my logic. I show those coils. So basically, this would be my more button. Some of the rules, and some of the rules for the less would be to turn it off. So there's a bunch of rules in here, there's a bunch of rules in here, and I would need to know all the logic. If I'm in auto, what it would be. If I'm in manual, what it would be. Okay, so if they're all off, and I don't know which one to turn on next, I have to know which was which one was the one that turned on last. So I have to have logic for turning on the, okay, so the starting, which one was, so I'd use the start logic to start the pump, and again I can use seal circuits or I can use set reset. So the start, pump 1, and this would be pump 1. This would be to start. This would be to stop. That use set reset logic. Now I need to know which one was the last one to turn on, so I need to take this pump 1, positive edge, and take it to a memory circuit. So it then says a set reset circuit. And the reset would be pump 2 or pump 3, the leading edge. So the leading edge of the other two would turn it off. So this would says the last one on was pump 1. You need to know that in order to have this logic up here. So who was the last one that turned on? If they're all three off, who was the last one that turned on? You need to know that in order to say which one starts, which one of these pumps to start, or which one of these pumps to turn off. Okay, so that sets up a series of rules in here, and then you have coils that says turn on pump 1, turn on pump 2, turn on pump 1, turn off pump 1, turn on pump 2, turn off pump 2. Then you have a memory circuit for pump 1, a memory circuit for pump 2, and a memory circuit for pump 3. You also have an auto manual circuit. So I have basically a switch that says pump 1 is in auto or pump 1 is in manual. So pump 1 is auto or pump 1 is in manual. So auto, manual for pump 1, seal it or reset it. You have to do that for pump 2, pump 3, and then you have to incorporate that into your rules as well. So there's a lot going on, but it can all be done. And that is basically all I can give you, except for the intricacies of these rules, and there's a lot of them, so it takes time. I wish you the best. Take care.